So, in case you all hadn't noticed before, the universe really is an amazing place. There's so much to discover, and today we're gonna reach out and look at one particular thing. It's something that we don't encounter as much in astronomy, but it's really, really interesting. Today we're going to look at magnetic fields. And not just magnetic fields, we're going to look at magnetic fields in the furthest reaches of the cosmos. We're going to look at them at the largest scales possible of our universe. We're going to talk about chasing cosmic turbulence, the secrets of magnetic fields in clusters of galaxies. What that has to mean, we'll see in a minute. So what you're seeing here is an image that's become a little bit famous over the month. This was actually revealed by President Biden in July. It was one of the first pictures that the James Webb Space Telescope took of the universe. What you're seeing here is a galaxy cluster, the thing we're going to talk about today. You see different types of objects on this image. And you see, for example, these star-shaped dots. These are actually stars. Not of other galaxies, no, stars of our own galaxy. We're looking through the galaxy of our own to the cosmos beyond. And what do we see in the distance? We see two other types of objects. More vague blobs instead of pointy stars. We see white and yellowish blobs. These are galaxies. They're all part of one system, the galaxy cluster. A cluster is a large group of galaxies containing 500 to 1,000 galaxies apiece. In the background you see other blobs. You see more reddish and orange blobs, and these are also galaxies, but they're much, much further away than the whitish and yellowish galaxies in the front. And so we're really looking at a galaxy cluster with a background of red and orange galaxies. Now, what is a galaxy cluster? If we zoom out from the Earth and go to the largest scales of the universe, we encounter something that is called the cosmic web. On the largest scales, we find these large masses of galaxies clustered together, these galaxy clusters, that are connected by large bridges of gas and galaxies. And these bridges are called filaments. You can really imagine this as a cosmic web in which there are spiders in the center of these galaxy clusters. And in between the web, there are large voids. In the voids, you don't see as much. You don't see many galaxies at all. And this is the largest scale that we know of in the universe. This isn't static. This is all moving. But we don't live long enough to see this evolving over time. If you would speed the clock up, then you would see that everything is moving slowly towards these large clusters. Everything is slowly being pulled in by gravity. And these galaxy clusters don't only contain galaxies. While galaxy cluster contains galaxy, obviously, there's also something else. Something that's really invisible unless you look in X-ray or radio wavelengths. It is the ICM, the intra-cluster medium. It is a kind of really hot, and I'm talking about 10 million to 100 million Kelvin gas, that's ionized. So that means that all the electrons and the ions are moving freely through each other. You don't have atoms. They're really low density. And with low density, I mean one particle for every liter of ICM. That's something we just can't fathom here on Earth. It's something completely different than we're used to. And in between these galaxies, there's not only this really hot diluted gas, there's also magnetic fields present that run through this ICM. Now, on the top left, you see the pinkish glow of this ICM in between the galaxies, as seen by the Canberra X-ray Observatory, which obviously sees X-rays. But on the bottom right, you see a different galaxy cluster, which shows an interesting structure. If you look closely, you see these small bubbles that are being blown. This is because in the center of these galaxy clusters, there are galaxies that are spewing out material, really hot material, that's blowing away the ICM in the center. And not only this causes interesting structures, also when two clusters collide onto each other, really interesting sloshing happens, which will over time turn into turbulence on the ICM and will cause interesting things. This is actually a simulation of how the ICM looks like, the density of the ICM. You see all of these small whirling structures, the turbulence, which really means that the ICM is really complex, not gas, but plasma. So what happens when two clusters combine and collide? Well, the galaxies inside of a galaxy cluster are far apart. And this means that if two galaxy clusters combine, they collide, the galaxies can just move past each other. However, that's not the case for the ICM, because the ICM fills all space in between these galaxies. And so we can again look at a simulation of what happens when such two ICMs collide onto each other. On the right you see one ICM of one galaxy cluster, and if another piece of ICM collides on it, you get these really interesting turbulent structures. And this turbulence adds to the turbulence that's already present in such a galaxy cluster. And this turbulence means that there's a lot of movement of particles, even on the large and small scales. And movement on small scales is nothing else than temperature. This means that if two clusters collide onto each other, you get more turbulence and thus higher temperature of the ICM. Not only that, I talked about the magnetic fields in a cluster. Well, what happens to them when you've got a collision? On the bottom, you see the magnetic fields. And what you see is that they get stronger at the front where such a collision is taking place. This means that a collision between two clusters strengthens the magnetic fields inside of the cluster. And that's really interesting, because these magnetic fields, they contain a wealth of information about what happened in the past of such a cluster. Maybe we can see signatures of outflows and galaxies in the center of these clusters. Or maybe we can see where the ICM has been shocked or is sloshing due to a collision of another group or cluster of galaxies. However, there's one problem. We can't just measure a magnetic field of a galaxy cluster. You can't just pull out a long stick and stick it into another galaxy cluster. It's really far away, and yeah, you wouldn't be able to measure it. We need a different method for this. And then I come to radio astronomy. Radio astronomy is a really interesting type of astronomy, but it's not your regular looking through a piece of glass astronomy. Because of this, we need to think a little bit about what does a radio telescope do exactly. Well, we can think of such a large dish as not looking at the universe. It's rather listening to the universe. Radio astronomy is like listening to the universe instead of looking. This is because this whole signal, this whole wave that's coming in, we can capture. We can measure all information in it. Its amplitude, the wavelength, the direction it's coming from, even the direction in which it is waving. However, you can ask the question, okay, but if radio astronomy is just listening, how do we make these beautiful images of the sky with radio telescopes? Personally, I didn't understand this as a child. I was really into astronomy and stuff, but I never understood how radio telescopes can produce such beautiful images just by capturing some random signal from the sky. And to explain this, I would like to do an experiment. Is there maybe someone from the audience? Oh, that's a coincidence. Really interesting. Okay, so you can stand here and just face in the direction of the public.
Yeah.
So we have something very similar to a radio telescope on our head. What do you think it is?
Ears.
Ears, exactly. Very well. Okay, so we can do an experiment. Let's see if you can make a visual image of sound without looking.
Okay.
So if you close your eyes,
Yeah.
I'm going to ask you, where do you hear me clapping in the room?
Okay.
And please point towards that direction.
Okay. Somewhere here.
Okay.
Over there. Okay, it's gotta be there. I just stand behind me and from the other side.
Okay, thank you. You're a really good telescope. You're
Yeah.
really good radio telescope. Yeah. Let's see if you can also make an image. I'm going to give you two options. Either I'm drawing a circle in sound, or I'm drawing a line in sound.
Okay.
Are you ready?
Yeah.
Now the second one. That's a line?
Kind of went like this, I guess.
Circular or line?
My bet would be line.
Okay, a little bit more difficult, yeah. So I actually tricked you. I made 2 circles.
Oh, 2 circles?
Yeah.
Okay, fair enough.
Okay, so, but you can like have an idea of how you can make a visual image. Do you have an idea how our brain is able to do this?
Well, basically from the direction, I'd say.
From the direction.
Yeah.
And how does the direction of sound influence what we hear?
I'd say, first of all, I can hear from which side it comes from. And secondly, it's how loud it's coming from.
Okay, so how loud is certainly one thing.
Yeah.
You can sit, thank you very much. Please, so the main mechanism in which our brain works is that it can capture the time difference between both ears. When a sound is here, it travels through the air at a large speed, but it travels first across this ear and then across this ear. And from the time difference, you can actually say where the sound is coming from. And this is exactly how a radio telescope works. If you add not 1, but 2 antennas on the ground, just based on the time difference between a signal arriving in one dish and the other dish, we can actually make an image of what we're hearing on the sky. Now, I was not using a radio telescope based on 2 dishes. I'm actually using 64 dishes. How could we maybe simulate that in this room using 64 dishes? Well, I think we have about 64 people here. So let's go and maybe create the first human radio interferometer and try to find a way to visualize this. Okay. So before the talk started, we put someone in the audience who's going to clap once. You need to be very, very good listening. And I'm giving you one instruction. It is to close your eyes. And when you hear the clap, in a few seconds, slowly, not fast, point in the direction you're hearing the sound. If you move too fast, you're going to hurt somebody in your vicinity. You're not going to do that, okay? So, if everyone could please close your eyes. And now someone from the audience is going to clap, and you're all going to point in the direction you're hearing from. Wow. Okay, you can open your eyes. And please keep pointing. Everyone is pointing in the same direction, approximately. And this is exactly, or almost exactly, thank you, can stop pointing now. Almost exactly how a radio telescope operates. By adding more and more and more dishes, we can make the fidelity of an image higher and higher. And we can say more about where a certain signal is coming from. I was using the MeerKAT radio telescope. It contains 64 dishes, almost the same amount as there are people here today. And it's located in South Africa. It's actually called after this cute animal, the MeerKAT. And the full array is a little bit larger than the room we're standing in today. It is 8 kilometers across. And each dish is 13.5 meters across. That's really large. And using this telescope, you can make beautiful images. As I said just a few seconds ago, a radio telescope doesn't just look at the sky, it can listen. And this means that all parts of a wave can be captured by a radio telescope. One of those things is not just the amplitude or the direction it's coming from. No, something that's waving also always waves in a certain direction. If a radio wave is incoming towards you, you can say that it has a polarization, which is actually just the direction something is oscillating. In this case, it's vertical. This is a horizontal polarization coming towards you. And we're going to use this polarization to measure magnetic fields inside of a galaxy cluster. Because imagine that there's a radio wave incoming from a distant source, like the red sources you saw on that first image from James Webb. It's coming in and it's hitting or traveling through a galaxy cluster. Inside of this cluster, there are magnetic fields in the ICM. And now something very strange happens. as this wave travels through the ICM, it changes direction. So you can imagine if this wave starts off, first it's waving up and down, and then it encounters these magnetic fields and it starts waving in a different direction. And this direction doesn't just rotate a few degrees, now it can really rotate a few times before it reaches us, the Earth. And what's really cool about this is that the stronger the magnetic field, the larger this effect becomes. So by looking at the amount of rotation of such a radio wave, by listening to it, we can actually say something about magnetic fields in a cluster. Something that's really difficult and wasn't really possible before. Okay, there's one problem. As I said before, the ICM is really turbulent. This means that the magnetic field isn't nicely ordered. It's not all pointing in the same direction. If such a radio wave encounters a magnetic field that is pointing in the same direction as it's traveling, it actually rotates, for example, anti-clockwise. When it encounters a magnetic field that's pointing in a different direction, it travels back, clockwise. So what's possible is that it first starts rotating this way, and then this way again, and at the end we end up with zero, nothing. Well, that's really difficult, because just based on the direction of the wave that we're seeing, we can't just say something about the magnetic field strength. Because who knows what this wave has done throughout such a cluster. Well, there's one trick we can use. Imagine that one of you tonight drinks way too much beer. Yeah? We give you free beer to do an experiment. And we put you here outside of this cafe in the middle of Leiden. Tomorrow the police will find you on the side of the road, and we can ask the question, how far did you travel in this time? Well, as a drunken person, you'll never run straight. You'll make different ways throughout the city. But you could, for example, find yourself somewhere in this red circle. We can repeat this experiment 100, 1,000 times. And on average, you could say that someone could be found in this circle in Leiden. However, you could now ask the question, is there a relation between the size of your beer belly when you start at the evening and the distance that you've traveled on average over the night? You can imagine that someone with a large beer belly will probably reach the red circle, and someone with a smaller one will reach the blue circle. And exactly in the same way, we can do this with our galaxy cluster. We don't know the exact relation between magnetic field's strength and rotation, but a rotation that's really large probably on average has encountered larger magnetic fields than one that doesn't. So you need to do statistics, which is really boring, and I'd rather talk about drunken people traveling through Leiden than statistics. And so this is exactly what I did in my bachelor thesis, ferry rotation of radio sources in Able 85. Able 85 is the name of the galaxy cluster, using the MeerKAT galaxy cluster legacy survey. And I did this with Clement van Beek and Erik Ossinga, who's also in the room here today, so I need to be careful not to make any mistakes. So this whole trick that I'm explaining now depends on a few things. You need to have these magnetic fields, which is obviously probably the case for all clusters. But you also need to have these background sources, of which the radio waves need to travel through the cluster and reach us at the end. And here you're looking at a VLA image that Erik Ossinga, here present today, made or requested. I'm not sure. Did you actually request this?
No, I made it. Yeah.
He made it, yeah. So this is an image that he made with the VLA. It's a humongous telescope in New Mexico. However, over time we built better telescopes, and the data I got my hands on goes from this, with just a few blobs, which are actually the galaxies inside of the cluster, to this. And now we see a lot of background sources, which are really faint, and we can use them to measure the polarization and the rotation, and from this, the magnetic fields. And ta-da, these are the results. The right plot is a little bit more difficult. It shows not the rotation over the cluster, but it shows the decrease of polarization strength, which is something I didn't talk about. But what was interesting, for example, is that you can see that in the center, there's more spread in these points than in the edge. And I've got a better plot on this in the next slide. But on this side of the galaxy cluster, there were some interesting points. There are five points that are really high in depolarization. So the weakening of polarization. And this indicates that there might be an inflow of clusters, causing higher turbulence, stronger magnetic fields. And so what was the main result is actually this. Magnetic field was strongest in the center of a cluster and was most turbulent in the center of a cluster. This is actually what we expected, which is really good, but we never measured this for a single cluster on its own. And here you see the radial profile. This is the distance from the center of the cluster. And from this slope, we could already see a little indication that the magnetic field is strongest in the center, and also that it's most turbulent in the center. This is again based on the weakening of polarization. So, after half-year work, this is the result. And yeah, I had enough, but Erik is still probably working on stuff like this. So, thank you very much for your attention.
Do you have any questions?
As a layman in this area, I would like to know whether the magnetic fields are entirely due to electrons.
Okay, so the ICM is really hot. This means that it's totally ionized. The electrons and the protons are freely moving through each other, right? The question, I don't know if everyone heard it, the question was, why do these magnetic fields exist? Is it due to the electrons that are moving? Well, in middle school, or I don't know where everyone learns this, but you probably have heard that moving electric charges induce a magnetic field. And in the same way, moving magnetic fields, changing magnetic fields, induce the moving or changing electric field. And those two keep themselves in balance inside of the ICM. Because there are so many free charges that can move any direction, whenever there is a magnetic field, it will cause electrons to go flowing. And the flowing electrons then maintain the magnetic field that was there in the first place. And because of this, you get a steady state. So it doesn't change over time. If you put a magnetic field inside the ICM with these charges, they start moving in different orbits around these magnetic fields. And this sustains the magnetic field. Meaning that if you do nothing, the magnetic field would just keep on existing as they do. So, sort of, the answer is yes. The electrons maintain the magnetic field, but they don't create it. Is that?
May I ask the follow-up question?
What did create it?
What does?
Ah, that's really interesting, because we don't know.
At least that's an honest one.
That's an honest question, and we have theories, but we don't know. One really interesting theory is that the Big Bang also spit out some magnetic fields, which then were omnipresent throughout the universe. But they were really, really, really weak. And due to this turbulence, these magnetic fields gained strength and got to the levels that we can see today. But I need to stress that these magnetic fields are still incredibly weak. They're micro-Gauss. Our magnetic field on the Earth is half a Gauss here in Leiden. So that's really little. Yeah.
So, first of all, I was wondering, you showed us the final results of your thesis,
Yeah.
but you didn't tell us what they mean.
Yeah.
So, I congratulate you for your results, but I'm super curious now. You kept us hanging on a cliff. So did you get any conclusions about some kind of very strong magnetic field in the center of the owl cluster? Is there like a supermassive black hole there or something like that? Like you mentioned something that is in the description in the Facebook page. So is there any connection to that?
Okay,
And
so
I have a follow-up question.
yeah, thank you. Thank you for the question. So the question is, what more can we say exactly about this cluster based on the results that we have here? So as I explained with the drunken man here in Leiden, we can't say anything about someone's beer belly just based on one route that he or she traveled throughout the night. We need many different experiments before we can say something about this. And so we can only say on average that in this distance range, if we count all data points together, there's a larger spread in rotation in the end than that there is for a similar sized bin here on the right far away from the center of the cluster, meaning that the magnetic field probably is strongest here and the turbulence probably is strongest here compared to the outskirts. But you can't really say something about the exact positions throughout the cluster, and if these AGNs, supermassive black holes, are spewing out material that's inducing a magnetic field in the ICM around it, we wouldn't be able to say this, the amount of sources that we have right now. But maybe when the square kilometer array arises, we would be able to say something like this. I don't know yet.
So the other question was from somebody who couldn't be here today.
Okay.
And he read the description that you gave on Facebook page.
Mm-hmm.
So, but I'm not sure if, so please let me know if the question is not related to your field,
That's
your
okay.
research.
That's
so,
okay.
because it's more about primordial black holes. So he says like this. He says, is it possible that the hypothetical black hole stars, if you heard of them, could provide an explanation for the James Webb Space Telescope data that shows higher than expected metallicity in high redshift galaxies, so very distant galaxies, as well as the mass of the supermassive black holes in the modern universe. So he's asking about, yeah, do you understand this?
Yeah, so the question is on primordial black holes and the result of primordial black holes, which is just a theory right now, on the results from the James Webb Space Telescope. So I would recommend you to write a letter to the observatory of Leiden, because it isn't exactly the topic of this talk, but I'm very sure that there are people who are willing to write down their own opinion on this. But remember that it will probably be a scientific opinion because we don't know about these things exactly at the moment.
Yes.
But yeah. Thank you. Thank you for the question. Okay. Is there-
There's a question there.
Ah,
Yeah. Do you need to make any assumptions on the initial polarization of the light before going through the cluster?
oh, we're going down that rabbit hole again. Yeah. So we measure a direction of the radio wave. But now you can ask the question, how do you know the original?
Yes.
How do you know the
Do
original
you make any
direction of the radio wave? Well, really difficult question. Well, luckily there is a semi-easy answer, and that's that I didn't tell the whole story. Very long wavelengths are really susceptible to this effect, meaning that the same strength of the magnetic field will have a large effect on large wavelengths. Short wavelengths aren't affected that much. And since I don't just look at one wavelength with the MeerKAT radio telescope, I can use the shortest wavelengths to see what is the original direction of the polarization. And I can use the longest wavelengths to pinpoint the change in orientation. So by using multiple wavelengths, I can pull these two apart, the original orientation and the rotation. So I don't need to make any assumption about the original polarization direction. Of course, this is astronomy, so that means that this is boat-loaded with a lot of assumptions, but this is important. Thank you for the question.
Sorry, you just mentioned wavelengths and this long wave and short wave.
Yeah.
Is this like expansion of the universe affecting these wavelengths as like?
Yeah, so everything is redshifted everywhere in the universe because everything is expanding. And I just said that we need to make a lot of assumptions. And one of the things that we're not taking into account here is the fact that when this wave travels through the cluster, it's also expanding. So it's also, you're actually probing different wavelengths throughout the cluster. A different thing is that I showed in the beginning this nice picture of the James Webb Space Telescope, and you saw that these background sources are all like lensed around the central mass. And that's something we also don't take into account. If we would do this correctly, we would need to make a little correction to the positions of all the sources in the background. So there's a lot we don't take into account, but it is a really small effect. I don't want to hear describe it now. So, but thanks for the question.
Okay, one last short question.
Yeah, I was just wondering, because you said that through magnetic fields we can learn something about the history of clusters.
Yeah.
I'm wondering why we learn about, like, do we look further back in the past if we only look at the magnetic fields, or because I imagine all we see in the magnetic fields is what we have right now, or compared to the drunken man in Leiden, all we see is where he ended up, like we don't.
Yeah. So the question is, how do we exactly know something about the history of a cluster just based on the magnetic field structure now, right? Okay, so it's exactly like after World War II here in the Netherlands. When you see a village that's completely destroyed and is in shambles, has a lot of turbulence, let's say, then we know that the Germans probably went through this village. Well, a village that was really like the same as before, didn't have any collapsed buildings, and you know the history of that village. Maybe that we got to defend it, or we just didn't bother fighting over it. So, to give an analogy, this is how you can think of it. You see the remains of what happened before, of the collisions.
And you only see that in the magnetic field and not in the other parts of it?
So I showed an image in the beginning of the X-ray, and you could also see these large voids that can also be used to study this. However, the thing is that you can't look into the turbulence of this ICM using this method. You can only see the large-scale structures, while with the magnetic fields you can really see how small these turbulent movements are that are caused by a collision. Okay, thank you very much.